All right. Thank you for coming, everyone. Today, I'm going to be talking about leveraging real-time data in financial services institution. It's talking about FSIs because obviously this is FinTech DevCon, but the principles that I'm going to talk about I've done across a number of industry verticals. So financial services, automotive, IoT, telcos. The same sort of principles that we're going to talk about here will apply across a range of industries. So I hope this is useful. There's a few things I'd like to say before I start. First is, this is a workshop. I'd love to keep it interactive. I'm going to, sometimes I'll ask questions. Sometimes I'd really like you to heckle and say, explain that, or I don't understand that. I appreciate that I am Australian. I have a nasty Australian accent. If I get excited about something, and as I present, I get very excited, I talk very quickly. It is difficult to understand me. So if I am talking too fast, please, please, please say, could you slow down? Thank you, thank you. No, that's perfect. I'm hoping you're practicing, but if not, can you put your hand up if you don't understand me? All right, that's a good sign. Okay, great, perfect. So keep this interactive, please. I'm not here to lecture at you. This is a workshop, and I'd like us all to learn something. I'd like to have some fun along the way. And if you all sit there and you're all on your phones and reading Facebook and things like that, I'm going to find this a very difficult presentation. So please, for me, any interactivity would be much appreciated. Thank you. All right, so who am I? My name's Tim Faulkes. I'm a developer advocate at Aerospike. I've been a developer for more years than I'm going to admit in a public forum, but let's just say that I'm very tall and I have hair at the front of my head but nothing else behind me, so I'm not going to show you the back of my head because that will show you my age. So really, I'm a developer at heart. I've been doing Java. I wrote my first computer game at age 11. I'm a true nerd. So, we develop applications, and when we develop applications, there's a lot of moving parts. There's people who specialize in different areas. I have done a number of applications, and they all look like this. There's a big front end, and everyone has a whiz-bang front end, and they're very fancy UIs. They're all doing really clever things, and there's a lot of appeal to that, to the business, to the end users. They really like the front end. That's a lot of where the interactivity comes from, and if I dare say it, the sexiness of the application is measured by how cool your front end looks. And then as a developer, I spent a lot of time focusing on the mid-tier. Okay, well, I've got to have all these services interact. I need to make sure that I can scale up and scale down and do all this resiliency. And there's all these tools out there that really help us. Kubernetes is a big one, isn't it? Put your hands up if you're using Kubernetes in your organization. Okay, a good number. Okay, so, you know, I started off developing these monolithic applications, and they had one big tier and you couldn't scale. And now we break things down into microservices. We develop all these workers and things like that. And everything works fine. And there's a lot of coolness in that because I can scale my infrastructure up and down. I can scale my applications up and down in response to load. And then as an application developer, you might notice over there, just on the right-hand side in a really tiny bubble, is a database. Because we don't really care about databases. We're application developers. We want to write applications and do cool stuff. And the database, at least in my experience, tends to be the last thought. It's going to store data and it's going to put data. And let me tell you, someone who works in a database company, someone says, I want a really cool demo on a database. It's like, here's a piece of data. There's a piece of data. It's really dull. But as application developers, if we want an application that is going to scale with us, that is the most important piece of the puzzle. All of this mid-tier is stateless. It's easy to scale up, it's easy to scale down. But a database stores your information, and if it goes down, even though it's not the sexiest part of your application, it is going to affect your performance. You know, we've all heard the stories on the paper of new game launched and suddenly it all went down because the database couldn't keep up. So what I want to do today is talk to you about big data. There are a lot of databases out there. Can anyone have a guess at roughly how many databases there are out in the marketplace at the moment? Take a guess. Did someone say 250? It's about, sorry? 1,000? Somewhere between 250 and 300 any day. 1,000 is about, there's probably a lot of small ones. They're all good. They all have a reason for being. Now, some are better than others, But when I'm going to do this, I'm going to talk about different databases and different needs and why you might pick one over the other. And it really comes down to your business needs. What am I trying to do? Now, if I'm writing an insurance application, I've done it, I'm not ever going to do it again. If you can do it, I really praise you. It's got slow data. It doesn't matter. If I'm underwriting an insurance claim and it takes me 10 minutes to get my data back, it's probably not the end of the world. But there are a lot of things, particularly in financial services, where we need real-time data. And this means different things to different people. I went into a financial services company a couple of years ago, and this was a big financial services company, and they said, we have big data and we need it really fast. And my first question whenever someone says that to me is, what do you mean? What to you is the definition of big data? And in their term, they said, well, we have 80 gigabytes of data and we want 1,000 transactions a second. And my inclination to pull my phone out of my pocket and say, here you go, here's something that can handle that load was very high. I didn't because I'm very controlled, but that to them was big data, and that's fair. But when I'm talking about big data, I talk about things that are bigger. So let's talk about fraud detection. It's a very common use case. We have a credit card swipe that comes in. What happens when a credit card swipe occurs? Well, the person who acquires the card will send it to the issuer of the card, and they want to know whether this is going to be fraudulent or not. So they take that credit card swipe, they get a bunch of information about it, and they want to load the history of that data. Now, if you're a data scientist, you will know that the more data you can load in the same time period, the better the result. If I can load 30 days of your history, it's better than 10, but 90 days is better, 180 days is better. But they also have a finite time window. So one of the credit card merchants I was working with recently, they have 120 milliseconds. From the time you swipe your credit card to the time they say yes or no, it's 120 milliseconds. If they go over that, they fall back to very simple rules-based or their AI goes out the window. So they want to load lots of data and they want to load it quickly. Well, in their case, they wanted to load 100,000 pieces of data in those 120 milliseconds. But remember, 120 milliseconds is end-to-end. That's not just loading the data. That is, I need to do my processing. If I can load the data in 119 milliseconds, it's no good to me because I can't process. If I can load it in 1 millisecond, then it's really good to me. That's very difficult to do. So that's what we're going to start talking about, big data, fraud detection. There's a lot of different use cases, things like Customer 360. It's not quite as real time, but there's a lot of data that you need. You're conglomerating information from a lot of sources, and you want to say, what recommendations would I show? I want to do predictive analytics. I want to do compliance if I'm doing trading. I want to make sure that I can check someone's trades in real time and make sure they're doing the right thing. For example, I've worked with a financial service institution who do lending on, they're a brokerage house. They do margin lending. But if you do penny stocks, you can't margin lend on them. It's out of compliance. However, if you're doing the validation on the mainframe and you're doing it in a batch once a day, that doesn't work. I could buy my penny stocks with a margin lend at 9 a.m. I sell them at 5 p.m. I've violated the rules, but I haven't been caught because the batch didn't pick me up. So they wanted to do it more frequently. So things where you need to do things faster and better. That's the sort of information we're going to be looking at. So the first thing to do when looking at a database is say, step back and say, what do I want this thing to do? As I said, there's hundreds of databases out there. They all have specific niches. There is no, in Tim's opinion, there is no single perfect database. If anyone says, I've got a database that will be perfect in every single case that you can come up with, I think they're lying. I haven't found anything that goes close to it. There's lots of good databases out there, but we all have niches. So when I look at a use case, when I'm coming into an organization or I've got a use case, first thing I do is say, what am I trying to do? What are my needs? And the first is it write heavy? Am I doing, say, IoT ingestion of data or stock market ticks where every time I have to ingest some stock pricing? Is it read heavy, like credit card fraud? Is it a mix? Is it a 50-50 mix? Some databases tend to be good at one thing. Some databases tend to be good at read heavy. Some are good at write heavy. Some are good at both. What happens about consistency? Now, put your hand up if you've only used relational databases, please. if you've only used relational databases. Okay, a couple of people. Okay, good. I know for a long time I used only relational databases, and the thought of using a distributed database was in its infancy, and it meant that we're all used to having a database there where it always has the data and it's always consistent. Under no circumstances does your data become inconsistent. But when we start talking about distributed systems and we want to have resiliency, so if we lose that one node that holds our database, we can still keep running. That's where it becomes an issue. What do we do if the data becomes inconsistent? And some databases are fine with it, and some use cases are fine with it. They want an answer, and it's better than no answer. If you're storing my credit card history, and you give the wrong result on a credit card swipe, it might not be the end of the world. But if you're storing my account balance and you give me the wrong answer, then it is the end of the world. Okay? There's all sorts of compliance things they have to make sure of. So a use case needs to know, can I tolerate inconsistent data? I'll come back to this a bit more. What about durability? If I'm using a monolithic system and that node goes down, I have no data, my application is dead. So this is why we start distributing the data around the world. We can distribute the data across a set of nodes, and we can lose different nodes in that. But then if we lose that zone, it goes down. What if we distribute it across multiple zones? That's great. But then if the whole region goes down, which encompasses all those zones, we also have problems. So do we need to make it multi-zone, multi-region? And sometimes the speed of light comes into play. When I'm writing data and I need consistency, and I'm doing this across different regions, the speed of light between those different regions takes time to send the data. It slows your writes down. So there's pros and cons of doing this resiliency. It makes you more resilient and I can tolerate losses, but it has a cost. What about the size of the data? Many people I talk to say, look, I'm just starting off small. I need 100 gigabytes now. And that's not a great question, because the question is, where are you going to be in 5 years? Where are you anticipating this growing up to? Because let me tell you, one of the most painful things I have done as a developer is take an application that was running on a database, watch that database fall off the cliff and go into a territory it can't handle, and then try and re-platform the database. Even if you do your architecture right and you put a database abstraction tier in there, it is a difficult and painful process. So don't do it. Start off where you think you're going to get to. Don't over-architect it, but choose the right technology for where you're trying to get to. Velocity of the data. How much data do I need to load? If I need 1,000 records a second, there's a lot of databases that can do it. If I need 100,000 records a second, it's a different problem. And what happens if there's variability in latency? I'll talk a lot about latency in this in a moment. And what happens if something unexpected happens? I'm running a news site and something terrible happens. The traffic to their news site doubles overnight because of some catastrophic and unpredictable event. Or the stock market crashes and everyone's trying to load onto your portfolio management application. Look at the spikes, look at where you need to get to. All right, so we're going to talk a little bit about the CAP theorem. The CAP theorem is a theorem by a guy called Brewster, and it basically postulates there are 3 pillars of a distributed system. One is consistency, one is availability, and the other is partition tolerance. Now, partition tolerance means if I'm in a network situation and the network breaks, my cluster that might have had 10 nodes in is now 2 5-node clusters. What happens? If I'm running on a monolithic database, it doesn't matter. It's either there or it's not, so I don't need to worry about consistency. So you can see that I have databases like Postgres and MySQL, single node systems. They're always consistent and they're always available, unless that node goes down, in which case they're not available. It's an all or nothing scenario. Most people these days don't like all or nothing. So we start talking about, I want a distributed database. So we have to have partition tolerance. That means that I now either pick consistency and partition tolerance or availability and partition tolerance, because the theorem says of these 3 pillars, you can guarantee 2 of them, you can't guarantee the 3rd. It's quite easy to prove, actually. Now, there's a good number of databases, and particularly the original NoSQL databases like Cassandra, used to be an AP database. They could do partition tolerance, but if a node went down or a network split happened, they couldn't guarantee consistency. Some use cases, that is fine. It's not as bad as people think. If I'm doing ad tech, I've worked with an ad tech customer and they said, look, if we lose 10% of our data, we don't care. It'll regenerate itself in 30 days. Financial services is a different kettle of fish. For financial services, we almost always want consistency and partition tolerance, and not everyone can do it. So you can see there's some databases listed which can do consistency in a distributed fashion. The other thing to think about when we talk about response times, it's really common for people to talk about your average response times. When someone says to me, my average response time is 5 milliseconds, well, that's great, but what happens to your other 50% of the customers? So you get 50% of your customers who get fast response times. What happens to the other 50%? Do you care about them? They go, yes, of course we do. Then you don't care about your 50%. What you need to start caring about is your 99% or your 95% or your 99.9%. These are your tail latencies. These are people who will get the spikes. And we are humans and we are become so intolerant of slowdowns. If a web page takes 2 seconds to load, you lose something like 30% of visitors to that website. So you want to get the data so that this hockey stick effect, these 99 and these 99.9%, you need to start caring about them because that will impact things. Now, what does 99.9% mean? It means if I do 1,000 requests, the probability is that one of those will hit that 99.9%. So, if my database is loading one piece of data, the probability of that person having a bad experience is 0.1%. However, what if I'm loading 10 pieces of data? What if I'm loading 100 or 1,000 pieces of data? You can see the probability there of them actually hitting that 99th%. So if I do 500 requests, so I'm loading 500 pieces of individual data, the probability of hitting that 99.9% increases to about 40%. Okay, the more pieces of data I load, the bigger that probability is. And remember I'm talking about fraud detection? Do you remember how many pieces of data I said we needed to load? About 100,000. That's what they want to load in that time frame. That probability goes up and up and up. So, this is a workshop. I'm going to be doing a bit of live coding later on. It's really terrifying, particularly as my IDE crashed just as soon as I was about to come down here. And we won't go there, but Tim had more hair and was taller before he started this workshop. However, what I wanted to do for this workshop was show different databases. So I have written a little database simulator. You can plug in workloads, and we're going to talk about different databases. If you want to follow along, you can download this from GitHub. It's free, it's open source. You can put in different workloads and say, this is what I want to test, and these are the databases I want to test on. And I'm going to show you how to add a new database onto that. We're going to talk about a number of different databases. Postgres is open source. Aerospike has an open source community edition. These are links to the particular databases that we're going to talk about in depth. Now, I ran a number of tests, and I'm going to show you some graphs. I'm going to talk about what I did later on in the workshop. We're going to change that tool that I said so that you can actually play with it and do whatever you like with it. But I did all the tests on the same hardware. So when you're benchmarking something, if you're doing a comparison between different databases or two different things, whatever you are doing, make sure it's on the same hardware. You're doing an apples to apples comparison. So I ran it on this configuration. Of the 4 databases I'm going to talk to about, 3 of them are distributed. They're designed to run in an environment which has networks between them. If that network falls over, they'll stay up, they'll keep doing good things. However, Postgres doesn't. Now I know you can get add-ons for Postgres which will allow it to do, but I just wanted vanilla Postgres. So I didn't put any replication on these databases. So everything's basically running on a single node. If I wasn't using a database, I turned it off. It's only fair if something's sitting there consuming 100% CPU and when I'm not using it, let's turn it off so we can get an apples to apples comparison. I was really bad in my testing methodology. Whenever you test something, make sure your test harness is on a different machine to the actual thing that you're testing so that the test harness doesn't take CPU. I couldn't do that. I only had one really nice machine to play with, so I put my test harness on the machine that I was testing under load. But it was constant across all the databases. Okay, and what I wanted to load, I wanted to load about 50,000 users. So I'm talking about credit card fraud. 50,000 users with up to 30,000 transactions per user over a 30-day period. So they're doing about 1,000 transactions a day. Now, I was working with one of the credit card processors, and I said, well, how many transactions does the average person do? And they said, well, the average person might do, say, 20 credit card transactions a day. I said, so 1,000 seems a bit excessive. The biggest people they dealt with was about 250,000 transactions a day. So corporations will do massive amounts. So these are reasonable for consumers. They get bigger. All right. So my little testing application, I wrote this. Please critique it. Please throw stuff at it. If you really don't like it, please contribute a pull request and tell me what you didn't like and fix it. It's all open source. I'd love the collaboration. So what it's going to do is we're going to implement different workloads. So I'm going to be able to, I've put 3 of the databases in. We're going to add a 4th in so I can show you how to do it. And what it's going to do is you create a connection to the database and it has a set of workloads. You run the workload against that database. You can pause them, start them, stop them, do all sorts of good things. It will monitor latency and throughput on the UI, and it's really easy to connect to different databases. So we'll play with that. If you want to download it, I'm a Maven person, so you can download from from Git, clean it, and build it. It should work really well. And then we just go to a port. And I'll demonstrate this live. Not that that's a terrifying thought or anything. All right, so I'm going to talk about 4 databases. Now, only 4 databases, and I said there's 250,000 out there. I've picked on these 4 for reasons. I'll explain why in a moment. I'm expecting people to say, well, what about Scylla? What about Cassandra? What about Neo4j? These are all good databases. I'm not trying to write them off for any reason, but I couldn't test 250 databases. It just wouldn't work. So Postgres is a single monotonic system. It works great. It is an old, reliable database. It is probably the most common open source database at the moment. And certainly the fastest growing, I would say. Yugabyte is a distributed database which has Postgres. It looks and feels like Postgres for all intents and purposes. Postgres isn't scalable because it sits on a single node. It can scale as you grow that node, but after that it becomes harder. Redis is a good database, but it stores everything in memory. So it's not as super scalable because once you exceed the limits of memory, it becomes expensive. It's good at a couple of terabytes. As I start talking tens of terabytes, hundreds of terabytes, or petabytes, I'm not going to pay that in DRAM. That's too expensive. And Aerospike's more scalable and it's distributed. So why did I pick these ones? Each one of these databases has pros and cons. They are all good. So Postgres is very well known, but it's single system. Yugabyte DB is 100% Postgres compatible down to stored procedures and everything. They took the Postgres layer and implemented it on a distributed system. But Postgres has an architectural problem. It's not super scalable in terms of it uses processors. It hasn't got threads in it. So there's challenges there, and because of the reuse of that Postgres layer, it has inherent challenges. Redis is a great cache. As we saw on the CAP theorem, it's an AP database. And it's fast, but it's limited by the amount of memory. Aerospike is fast and it's scalable. It goes up to petabytes, and there's a good number of people in production in petabyte range, but it's not 100% open source, and if you use really small objects like 100-byte objects, it's fairly heavy on DRAM. So pros and cons to each of these databases. You might notice there's not a single cloud database on that list. I'm not saying these cloud databases aren't good. They all have good points. But every cloud database is closed source. So I want something where it's open source and you can download these and play with them. They're not multi-cloud. And put your hand up if your organization is multi-cloud or considering multi-cloud, please. Okay, a smattering of people. I'm finding more and more people I talk to, even if they're a heavy shop on one of the clouds, they're now considering multi-cloud strategy because of the resiliency and the redundancy there. So that's very common. And I couldn't do an apples to apples comparison. I wanted to run this on a single node. I can't do that with these databases. So that's why I excluded the cloud databases. All right, now comes the nervous part. This is where you can all heckle and laugh and say, haha, okay, Tim's going to fail this part. I have a simulator, as I said. I've got 3 databases in there, primarily Postgres and Aerospike, but because Yugabyte is so Postgres compatible, it can do Yugabyte as well. But I'm going to put Redis in there. So I'm going to show you live how to do this. And what I discovered about 5 minutes before I came down here to do my talk was that if I copy and paste my slides into my clips, bad things happen. So you might find that my indenting is really off, and that's because I'm going to copy and paste and I can't highlight code once I copy and paste it. If any of you is an Eclipse guru, I'd love your help. So, first thing we're going to do is we're going to install Redis and we're going to run a Redis server. Now, I've already done my brew install Redis. So I'm going to come here and very courageously do this live. And I'm going to stop sharing because otherwise you can't see my screen. Let's try that. All right. So I have a terminal and I'm going to run Redis server. So the first thing you need to do is, I'm on a Mac, so I do a brew install Redis. And it sits there and fires up. Okay, so now I've got Redis running. I've now need to go into my IDE, and I'm going to look at my POM file. And the one thing I need to do, that's legible, good. The one thing I need to do is make sure I have Redis plugin here. So I've already added this Redis plugin patch that just says I've got a driver. Now there's different drivers for Redis. People who are familiar with Redis probably used to Jedis, but Jedis is not a multi-threaded API. This is a multi-threaded API. So we're going to use this one instead, and it works very nicely. Then I've got these are my databases. So you can see I've got Aerospike, I've got Postgres in here. What I'm going to do is I'm going to come in here and add Redis in here. So I'm going to say I want to do a new class, and I'm going to do Redis database. And the first thing I'm going to do here, and I'm going to jump back to my slides so you can see that I'm going to show you how to do this. First thing I'm going to do is I'm going to tell it about a database and say, hey, I've got this database, I want to use it. So I'm going to put a database annotation on it. This is something that is part of the package I wrote. So it's not a standard way of doing this. You can't go and do this in your application. This is things I wrote. And I'm going to say my name equals Redis. And I've got to give it a version. So my version is going to be initial version. And then when I run my application, I'm just going to be able to see Redis will appear. So actually, before we do this, we might just run this. I'll show you what happens if we run this. Okay, so if I run this and then I bring up a browser and I go to my localhost 8081. Okay, you can see I've got my little simulator, time's ticking away, and when I start putting a workload on, it will show me latency. Now what I'm going to do is create a new connection, and if I look in my database, I can see I've got Aerospike and Postgres. So the aim of what I'm trying to do now is I'm trying to put Redis in that list there so I can run the same workload on Redis versus other things. So I've got a Redis database and I need to implement a particular interface. And I need to tell it how do I connect to a database. So Redis has a Redis connection. And then I jump back to my PowerPoint because I don't remember all the code. When I connect to Redis, there's a couple of things I need. So Redis needs a host and a port, it needs a password. And so what I'm going to do is I'm going to allow the user to enter these. So I need to tell it, I'm going to give it some config items. And those will appear in a UI box, which allows me to create a new Redis connection. And then I need to tell it how to connect to the database. So if you look at the Redis help, it says, hey, I want to go and talk to this Redis client. So what I'm going to do very cunningly is come out of that and copy and paste that code. And this is where Eclipse starts throwing errors at me and it gets very nervous. So I'm going to copy and paste this and put this here. Now I would fix the indenting, but if I did that, bad things happen. So we're just going to do that. We're going to save that and organize my database. Okay, and there's a few missing functions. I need to tell it how to run my workload. So I'm going to add those methods in. And then the next thing I need to do is tell it how to insert a credit card. So there's a credit card insert here. I just need it to actually connect to the database. So because Redis only allows you to have one key, one value, a credit card has lots of information. So what I'm going to do is store it as JSON. I'm going to take all that information and put it as a JSON object and put it in. So I'm just going to copy this and put it in here. All right, now if I organize my imports. Thank you. I'd love to be able to fix my indenting, but it's not going to let me. That's going to be database connection. And the one thing that really broke when I copied and pasted is that I can't select code. I can't move everything, so I don't know why not, but copying and pasting from PowerPoint into Eclipse is not a good idea. So hence why I'm doing this manually and moving cursor in all sorts of weird ways. I'm actually moving my cursor and, oh, now it's working. Look at that. All right, so we're going to try that, and now that should, as I said, live coding demos, never fun. What's the problem here? Equals hose. And it's got invalid characters, of course. Okay, so copying and pasting here is not a good idea. It's put in a whole bunch of invalid characters, which is not what I wanted in a live coding demo. I did this in Google Drive originally, and it worked beautifully, and then I put in PowerPoint. So, I think these invalid characters are going to, yes, there's a lot of invalid characters. All right, I was going to show you that now I can go and press the button on this, and it works beautifully, and here's Redis, and it works really, really well. It's not worth the time to go and fix the invalid characters errors. I apologize, I tested this under Google Docs, and it worked beautifully. So, let's just assume that that put Redis in, and we can now test Redis. We can do the other databases, but Redis is not going to work unless I fix that, which would take too much time. All right, so let me move on. All right, so we have 2.5 databases. Two work really well, one has invalid characters. I want to measure things. So one of the things you'll notice when I ran the simulator is that it measures a bunch of things. So I can create things, but it measures the 95th percentile and the 99th percentile. As I mentioned, the average is not what you want to measure. If you're measuring average, you don't care about half your customers. So what I want you to do is start looking at the 95th and the 99th percentile. But how do I measure 99th percentile? How do I measure 95th percentile? Well, remember that 99% means that if I've done 100 samples, I want the 99th of them. If I've got sorted data, this works really, really well. It's really easy to do. And we typically find the curve looks something like this. The latency hits a threshold. So if I want to get the 99th percent, I've got 1,000. I sort the 1,000 items and I pick the 990th. That's great if we're doing 40 samples a second. What if we're doing 100,000 or 1 million samples a second? That sort is too expensive. We can't do that. So, how do we do this? What we're going to do is we're going to estimate. So what we can do is, instead of sorting our 1 million samples a second, we're going to effectively put it into buckets. And we're going to have a set of buckets, and we're going to break these buckets down. Now, I've put my smallest bucket as 100 microseconds. If you're getting data back faster than 100 microseconds, I'm going to call it 100 microseconds, but congratulations to you, particularly if this is a distributed database, because a network hop across is about 100 microseconds, and read off an SSD is about 100 microseconds. That's a really, really tiny number. And then after, I'm going to have powers of 2. So I'm going to multiply it by 1.414. I was a maths nerd in high school. I apologize. But we're going to start multiplying it by incremental buckets. So each one will be 1.414 times bigger, or root 2, and we're going to keep going up and up and up. Now, when we get a sample, what we're going to do is we're going to work out which bucket to put it in. I went up to about 60 seconds, and I had about 40 buckets. So that was a very low cost. Every time I get a sample, I'll put it in the right bucket. The more buckets you put it in, the higher the computational cost, but the more accurate. So I'm going to I'm going to do a running tally. How many samples have I got over the total samples? Gives a percentage at the start of this bucket. So if I'm at this point here, I'm on my third bucket or whatever, if I have 50 samples there and 100 samples in total, I'll be able to work out the percentage at the start of that bucket. If I move on to the next bucket and I've got 75 out of 100, that'll be the 75 bucket. I'm going to use linear extrapolation. If I'm between two buckets, which I almost always am, I will linearly extrapolate between the start bucket and the end bucket, and that will give me a rough estimate of the 99th percentile at that bucket without having to do a sort. So these calculations are inaccurate, but the more buckets you get, so this was, I used doubling the buckets to get that sort of curve, then I used root 2 to get that sort of green line there. The more buckets you use, the higher the sampling rate, the better. You can efficiently measure it. So I can now measure the 99th or the 95th percentile without having to do a sort, and I can get a better accuracy on my calculations. So I came up, so these are some business requirements. These are real scenarios that a customer presented to me once. They said, we want to retrieve all the transactions for a credit card. We want 180 days of history, because our data scientist says that's the best thing for us. Our largest customers do 250,000 transactions a day. Their average credit card transaction was 6 kilobytes in size. Anything wrong with this? Anyone see a problem there? Sounds good on the surface, doesn't it? Well, let's do a bit of maths, because as I said, I was a maths nerd. I did a bit of maths of this and said, hang on. Let's consider one new transaction comes in. Well, I have to load 180 days. Each day, they did 250,000 records, 250,000 transactions. Each one of those transactions is 6 kilobytes. So for one day, one transaction coming in, 6 kilobytes times 250,000 times 180. That's 270 gigabytes you're loading for that one transaction. That's one transaction. How many are they doing a day? 250,000. Multiply that by 250,000. They asked me to load 61 petabytes a day just to say yes or no on a particular credit card transaction. I'm sorry, that's a little bit excessive. I pointed out the number of network adapters they would need just for this, and they started going, actually that's 781 gigabytes a second for one customer to load their fraud. It's not possible. So we challenged the business requirements. We said, this is not possible, this is why. What do you really need? What would make the most sense? And they came back and said, all right, well, let's think about this. What if we limit it to 30 days and we want you to load up to 50,000 records? After that, that's good enough. 50,000 most recent records. They have to be the most recent records. We can do hundreds of thousands a day, but we're only loading the 50,000 most recent. Our end-to-end SLA, as I mentioned earlier, is 120 milliseconds. This includes the AI on top of it. This isn't just data load, this is the AI on top of it. And you have to make sure that the more time you can leave for that AI, the better. So the more I can reduce the time of loading, the better it is. There are common ways you can reduce the amount of data in fraud. A common way is, I'm going to roll them up. I don't actually need the 50,000 most recent transactions. What I might want is the average spend and the average this and the average that, and I can average them over time. And I said, can we do that? And they said no. They wanted some stuff where it is, let's say, the location-based. So they said, we want those 50,000 data points of those locations, and we're going to find out the distance to each of those points and make sure that it's in the same sort of proximity, so that that gave them some better fraud processes. So we couldn't do that in this particular case. They said they wanted to start off doing 1,500 credit card swipes per second, but they want to scale up to about 10,000. And one credit card can obviously have multiple different transactions, so we had this sort of data model. All right, so the problem became well-defined. I did the maths and it was acceptable to me. So we went in and we started looking at what database should we use. We started talking about SQL. It's a good place to start. Now, if I'm doing a relational database, I'm going to model things and I'm pretty sure, has anyone here not used a SQL database? So everyone here is familiar with that you normalize, you do third normal form, you do fifth normal form, all that good sort of stuff. Okay, so we did the right thing and we did the right sort of normal form and normalization, and we end up with a credit card which had a account number, a PAN, some information on the credit card, and we had information on the transactions. So each transaction had a reference to the PAN, and I can have multiple transactions for one credit card. Now, this worked well. It was in third normal form. I had a foreign key between the PAN and the transaction and the credit card, and it worked well. But the problem we ran into, we were loading 50,000 records. Remember I said that that's the chance of hitting that 99.9%? So I'm loading 1,000 records, probability of hitting that 99.9% is 1 in 1,000. So if I loaded 1,000 records, it's 63%. If I load 50,000 records, I might as well call it a 100% chance of hitting that 99% latency. So we needed to be careful of that. So let's have a look at the simulator and what did it do? We ran the workload on these different databases, remember. So this was using Postgres. Now this was doing the data load. So there's two steps I took. The first was I'm going to load a bunch of data in, and the second is I'm going to do the fraud detection across it. So this is loading the data. Now you can see here that we've got some big spikes. So it's fairly common. The green is the average. But you can see this is the 99th percent, and this blue here is the 99%. So you see over time that it started getting worse and worse. Now that's not uncommon. I start off with great latency, so I know it's hard to read on the slide. This is the throughput. So that's about, I can't step outside my box. That bit there is 5,000 per second. But you can see it degrades. It degrades to about 1,000 a second. This is per credit card transaction. So 1,000 transactions isn't bad. I'm still doing okay, but my latencies are high. So let's look at the testing. Now, testing in a SQL database is very common. I did a prepared statement, I did the connections, got the results, all the standard sort of stuff you would do when you're writing a database. So this is very standard sort of database code. And I'm using every caching thing that I can, like prepared statements and getting data sources from pools and so on. So what happened when I ran? So this is a standard workload that's imposed on this Postgres database. You can see that it's reasonably good, but look at the latency. So if I'm looking at the latency here, the average latency there is about 150 milliseconds. The 95th percentile there is about 350 milliseconds. And this is for the whole end-to-end. I'm reloading a record, so a credit card, and I'm loading all the transactions associated with that. They have variable numbers, so I wouldn't expect a pure flatline latency, but it's pretty good. But the throughput was pretty low. It's about 40 a second, so that's about 40 a second there. Any problems with this in the scenario we're trying to do? What was our end-to-end window? Remember, our end-to-end window for fraud was 120 milliseconds. My average is just over that. So my average is 150 milliseconds. But my 95th percentile was 350 milliseconds. This is not going to work in this use case. Okay, and the reason being, I looked at the CPU. Those numbers there are all in the high 90s. So all the cores on this nice machine were being fully used by Postgres trying to grind away this data. So it worked, it just was not going to solve our problem. So my next approach was to do a NoSQL database. NoSQL databases are designed for speed. This was using Aerospike. Now, as I mentioned, in the CP theorem, Aerospike's a distributed database. So it has both an availability mode, so it's an AP, and a CP mode where it can do consistency. So this was using the consistency mode, so I was guaranteeing that the data would never be lost. Now, when I did that, I put the same sort of relational model in. So what I did, Aerospike supports secondary indexes, so I put in the same sort of data model and said, I want to put a secondary index on there. Now, this is going to give me the answer, and it's a very simple data model. It's very similar to what I'm used to relationally. Is it necessarily the right answer? Well, Aerospike's secondary indexes use scatter gather. So I've got 10 nodes in the cluster, and I say to all 10 in parallel, I need the answers for what transactions does this credit card have, and it'll give them all to me in parallel. The secondary indexes are stored in memory. They're very fast, but it'll bring them back to me in parallel. So that's good. I like parallelization. It uses all the hardware in my cluster very efficiently. The problem is that the results are unsorted. If I got 1 million back, I would have to sort them to get the 50,000 most recent. If these were small records, then I had memory issues, as I mentioned earlier. In the case of this person, they were about, or this company, they were about 6K, so that was fine. 6K is a great number. So the same data model that I used in Postgres, I used in Aerospike. What were the results like? Well, as I said, modeling identically. This number here is my average. Now the scale is hard to read, but that's about 15 milliseconds. So it's 150 under Postgres, it's about 15 under Aerospike. This is my 95th percentile latency. That's about 55 to 60 milliseconds. My throughput is about 600 transactions a second. Now remember we said we're trying to do 1500 and we want to scale up to about 10,000. This is on a single node, so if I use a cluster, this is going to be scalable. This solution is probably going to work. So my CPU is good. It's multi-threaded. Remember, Postgres is multi-processed, it's not multi-threaded, and therefore that's why all my CPUs were pinned. This one I've got two, one of which is my Java application, that's my benchmark, 142%, but my database about 315%. It's got 8 cores, so there's a lot of spare CPU. Where I'm probably bottlenecked here, and the important thing when you do big data is what is your bottleneck? What is stopping you go faster? Postgres was CPU. Here it was my SSD reads. I looked at the stats on my SSDs, and they were maxed out. So the SSD reads were taking a good amount of time. But if I'm using, I've got, as I said, that's about 95th percentile, 30 milliseconds. That's about 55 to 60 milliseconds. So even my 99% gives me 60 milliseconds to do my fraud detection, my 120 millisecond slice. So that's not bad. It's about 50% dead load, 50% of this. But can we do better? The problem we're hitting here in both of these scenarios is we're loading a lot of individual records from the drive. The probability of hitting that 99.9% is high because I'm loading thousands of pieces of unique information from the drive. That's hard to do. So, what other alternatives do we have? How can we make this data go faster? Let's think about SSDs. Now, I know an unfortunate amount about hardware. I'm a bit of a hardware geek. If I'm using an SSD, and everyone's using SSDs these days because they're faster. Everyone's got rid of rotational drives because they're big, but they're slower. The SSDs are faster. Everyone else treats them as a fast hard drive, but they're not. They're very, very different. Their reads are very different. Their writes are very different. When I read from an SSD, I have to read in 4 kilobyte chunks. So if my records are 100 bytes, I'm reading 4 kilobytes. There is no difference in time between me reading 4 kilobytes and reading 100 bytes with an SSD. 4.1 kilobytes moves 2 SSD reads, so I have twice the overhead. So I want to try and use that. I want to say these are small records. I want to make sure I group them and get the right sort of speed for them. I would like things that are similar to be grouped together. I don't want to be reading random records. If I can set this up so that I have the 50 most recent records all grouped together, I can do that in one read. That means that my probability of hitting my 99.9% is lower. I can group them together and do them in one hit. That's better for the transfers, it's better for the network, and it will give me a better result. So what I'm going to do is I'm going to group these records together. I'm going to conglomerate them. So instead of each individual record, I'm going to have a big set of records. The problem is there's trade-offs. Like everything I'm talking about, there's always a pro and a con. If I put too many records together, let's say I put 1 million records together, then suddenly I've got this really big thing that has to come back. I only want 50,000 of them, so I'm throwing a lot of information away. So what you want to do is try and find the sweet spot for the application. So most databases, including Aerospike, including Postgres, have internal data structures we can use. And I'm going to talk about Aerospike because it has a few nice things, and I'll talk about Postgres in a moment. So let's look at what internal structures we could use. Well, Aerospike has this concept of a map. So imagine a relational record, and when we're doing relational, we know that it has columns. Each column is a string or an integer or something like that. But with some databases like Aerospike, you can put maps or lists into each column. And that allows you to group things together. And the maps are very similar. They're like a dictionary or a map or whatever you're used to. They have different values. They have different keys. So I've got a key and a value. I can also do things by, I want to get by index. I want to get things by rank. I can store maps as ordered or unordered. So we're going to start storing things into a map. So let's look at our transactions. At the moment, we've got a credit card and we've got a bunch of transactions. Those transactions are individual records. What I want to do is I want to put the transactions into a single record, conglomerate them together. But when I do that, how am I going to store them? I've got lots of records per day. So what I'm going to do is I'm going to store instead of having just one transaction being its own record, I'm going to store a conglomerate with a credit card as the key and a day number. So I'm going to put all the transactions for one day into one record, which means that if I want 30 days, what I'm going to do is I'm going to go and load 30 different records. Now, this is effectively, if I'm doing SQL, I could do a select star where ID in, I can form my 30 keys. Aerospike is the same sort of concept. I can go and do this, and I can do these in parallel. So I can load those 30 days very, very quickly and know that I'll get all the records in that particular thing. So, how do I store them in this map? I've got a map that has my key for my day is my credit card number and the day that I'm using. I can compute the day, I know what the current day is, and I can compute my 30 days really easily. I've got my transactions. I'm actually going to store them in a fairly funny format. The first thing I'm going to do is I'm going to put the timestamp of this as the key, the timestamp of that credit card transaction as the key, and the data associated with it as the value. Why this format? Well, what I want to do is be able to do filtering. If I can do this, I can filter by the key. The timestamp is the key. So I want to say, let's say I want to read half a day. Instead of reading the whole day, I want to read half a day. What I can do is I can do something like, on my map, I can say get by key range. So remember, my time of that transaction is the key. I can tell it the start time I want and the end time, and tell it to give me all the data, and it will slice the data for me. So even though I've stored on the server everything together and the database will read the entire record, it will chop it up and just give me the parts that I want and send that back to the client. And this is very common across SQL and NoSQL databases. You have operations that say, I've got data conglomerated together, I only want part of it, just send me the parts that I want. And so we can use this to go and get some of it if we want half of a day for any reason. Anyone see any problem with this data model? I proposed this data model and they went, hang on, it has a problem. And they were right. What assumption have I made here? I've assumed that something is unique that I can't guarantee to be unique. What have I assumed? Well, this timestamp, what happens if I get two timestamps that are identical? Bad things happen, I'm going to start overwriting things. And I said, but you can't have two credit card transactions at exactly the same time. They said, aha. Apparently, if you go onto the Apple Music Store and you buy an album, you get 29 transactions that are stamped at exactly the same millisecond. Okay, good to know. All right, we're going to change our data model. We don't like that anymore because I don't like things that don't work and don't solve the problem. So what we did is we put the transaction ID as the key because the transaction ID is guaranteed to be unique. And then we put the timestamp as the first element. Now, remember before we sliced by the key? So we said, I want a range of keys. Now we can say I want a range of values. And some APIs, and Aerospike has one where I can say, I want a range of values. And it'll look at the value and say it's a list. And I'm going to take the first element in the list and work out what matches. So I'm going to do the same sort of thing, but I'm going to have it as a list of values. Now, this works really well. So what I can do is I can form my days to fetch. I effectively do a batch get. So remember, this is very similar to the SQL we saw where select star in. It's just loading a set of keys and getting the data. I'm getting all the items out of that. And this will give me that information. This will give me the results of, yes, I've done this properly, and show me what sort of information I've got. Okay, so how did that perform? Remember, what we've done now is we've taken all these individual records that we've done a secondary index query on, and we've gone and put them into conglomerates. We've reduced the probability of hitting that 95th, 99 or 99.9% because we're loading smaller numbers of records. Okay, so the graphs look fairly similar. However, the numbers are very different. The average latency was about 3 milliseconds. The 95th percentile is about 6 milliseconds, and that is about 10 milliseconds. So your 99th percentile was about 10 milliseconds. If you remember before, our 99th percentile was up at about 60 milliseconds. So just by conglomerating these records together, what we have done is we have removed 50 milliseconds from our 99.9th percentile. Suddenly my fraud window, the amount of data the time I have to run my fraud algorithm has increased. I went from 120 milliseconds, I took 10 milliseconds to load my data. I have 110 milliseconds to actually go and process that data now. So when we showed them this, we started loading more data. They said 60 days is better than 30. We can load more data. Our algorithms are better. So a lot of these problems that we're facing, and particularly as we look in the realm of big data, AI, IIoT, anything where you have lots of data and the more data is better, these sort of techniques are better. Then I went through and had a look and said, what are our bandwidth problems? What are our bottlenecks? In our case, the CPU was high, SSD's reads were probably the bottleneck. So if SSD reads are the bottleneck, how do I increase the performance on this system? If I said, this is good, but I want to move faster, how can I do that? I can put more SSDs in. SSDs have a read throughput, and they have a write throughput. It's not unlimited. It's fast, but it's not unlimited. I get better quality ones. They have higher reads. A nice one these days will do about 300,000 reads a second. The ones I'm using are about 50,000 reads a second. Or I could put more in and use them in parallel. And this gives... The other thing I would point out is, look at the lines. These are almost flat lines. Now remember, some of these credit cards had 10 transactions, some had 10,000 transactions. So I'd expect some variance. But this sort of linear predictability is great. If I go back to the Postgres results, oops, it was good, but there's jitter in it. So I can see that there's jitter there, and look at these spikes. So those are killers. They will say, these are going to violate my SLA, and they're going to cause me issues. What I want to do is try and get things so that my graphs look more like, oops, sorry, went too far now. This predictable latency is really great for your applications because you can say, this is what I want and this is what I get. I know that I'm going to get the same sort of results. Okay? And if I'm using a distributed database, then what I would do in a real scenario is I would test what happens when a node goes down, what happens when a zone goes down or a region goes down. I would test in a production-like environment to see what sort of times I'm going to get and then devise how much data I can load as a result of those under failure conditions as well. So my throughput here, remember I said they are at 1,500 and they want to go to 10,000? That's 4,500. That's on a single server. So there's loads and loads of scalability they can get here. All right, so a few thoughts I want to leave you with. In all the use cases that I've done, I created one test framework and it had exactly the same business requirements. It was testing different databases and those databases did different implementations. But the program was identical. It said, here's a credit card, here's a transaction, go and save it. Here's a credit card, go and load me the end most recent. And it was always identical. So you always got the same sort of testing. If you're doing a comparison, make sure you have a harness like that. Feel free to take this code and adapt it. If you're going to do any benchmarking or anything like that, it's very, very handy. So the object model was identical. The amount of records was the same. Postgres took so long to load the data and had such variability in it that I lost patience and I didn't put 50,000 accounts in it. I put 5,000 accounts in it. But the amount of data was the same, everything else. What varied was the database we're using and the pattern we're using. Now, I've shown you how to do that conglomeration in Aerospike, but when we look at something like Postgres, it can do things like JSON-B. It can store things together. Almost every database these days has ways of conglomerating information together so you're not loading as many records. We solved the problem at hand. We worked out exactly what the problem was and what we wanted to solve for, and we traded flexibility for performance. And that's a big trade-off. Nothing is free in this world. If you want better performance and you want to merge these things together, you have a more complex data model. It's harder to program to. It has less flexibility. If I want to query the data in another tool and it's slower, I can do it, but it takes a bit more work. So there is a trade-off. Knowing your underlying technology really helps. A lot of databases, and I used relational databases for years, and I had no idea how they worked. I knew about indexes, but I didn't know about how they stored things on storage or anything like that. That information is critical. If I'm using SSDs and I can choose to read 4 kilobytes instead of 10 bytes, it's going to give me way better performance, way better throughput. Grouping the data into a single record, we optimize the transfer off drive. And that's key. You have scarce resources, make sure you optimize them. What optimizations could we do? The best optimization is change your business problem. Remember I said that they couldn't conglomerate things and to do an aggregate on it? That would have been the best solution. I could have loaded a 10th the amount of data and I'd have a better choice of databases. As it was, they said we can't do that, therefore I was very limited on what databases I could choose. Even in their case, I could have argued and said, well, there's some of the data you can roll up and some data like your location data that you can't roll up. So I could put the stuff that I could roll up together and the stuff that I can't roll up together and use the best of both worlds. As I said, using SQL, things like Postgres and Yugabyte support JSON-B, Redis, Aerospike support maps and lists and things like that. So these techniques are fairly common across the different technologies. If I make my blocks too big, I'm putting a megabyte in, it slows me down. So there's always a performance curve. You have to know where you're forming on that performance curve and go from there. There are some databases that are really specific to the sort of application they like. So many databases these days, including, say, Yugabyte, operate on something called RocksDB. Now, RocksDB is an interesting technology, but it's really good on writes. Sort of pushes things in really quickly and then worries about them later. But the more writes you're taking, the worse your reads are until you compact the data. And that compaction takes time and CPU, and it gives you this variability and latency. So they're good, but make sure you test under a lot of different scenarios. I want to do reads, I want to do writes, I want to do this both at the same time. Compactions are often bad, and you'll see there's little spikes based on when you compact and the sort of compactions you do. This applies to Cassandra and Yugabyte and a whole bunch of different databases out there. Okay, so definitely a relationship between the size of the object and latency. Too small, you get wasted RAM, you get too many lookups, and bad things happen. Objects too big, you get too many disk transfers, can be slower for writes, and other bad things happens. One thing I didn't cover. I mentioned that we have 250,000 records per day in our biggest clients. Do you really want to put that into one record? I mean, that's a huge record, 6K times 250,000 records. When you write and you're updating that record, it's going to be slow. So sometimes what I would do is I'll take these objects and I will break them into lots and lots of smaller objects and keep them about 1 kilobyte. So I've put patterns on the internet like this adaptive map, which show you how to do that. It's useful. And I really want to say this. When you optimize, make sure you need to optimize first. A number of people who come in and say, oh, we can make that faster. And I go, why? It takes a millisecond. You've got 100 milliseconds. You're fine. Do what needs to be done, but nothing else. I want to say thank you. You've been a great audience. I really appreciate you sticking with me. I know this has been heavy and lots of theory and things like that. I apologize about my demo breaking. I'm going to blame PowerPoint because no one's here from Microsoft in the room, correct? Good, excellent. We're going to blame PowerPoint for this. Everything else worked beautifully. And I want to say thank you to Moov. To me, this has been an amazing conference. I've really enjoyed the interactivity with everyone. I think it's been really well organized and really glad they put it on. It's my first FinTech DevCon. Certainly won't be my last. So thank you very much. I appreciate you. And yeah, hope you have a great rest of the conference.
Thank you.
Thank you.